Okay, what we have here today is a crazy integral from MIT 2023 finals number 4. We have the floor function around the whole thing, 10 to the 20th, and then we have the integral of this from 2 to infinity with one mistake. This should be 48x to the 10th right here, all this stuff dx. Okay, when I came across this one about a year or so ago, I actually skipped it because I didn't think this was a fair problem initially. Just because I don't think I've ever done one where we've had the floor function around the whole thing. Usually we have the floor function inside the integral. I don't like how uneven this is either. Let's kind of straighten this out. The trouble I had is once we do this definite integral, we're going to have a number here, and then we're reducing it inside the floor. But what I got wasn't that clean, so I was like, this is kind of more of an estimation problem, and I don't really want to do a video on that. Well, when I came back to it the other day, I realized there's actually a pretty clean way to do it. So it kind of changed my feelings on this one, and I wanted to do a video. And so what I want to do to start is we'll just focus on the integral. We don't worry about the floor until later. And this is actually not too bad because you'll notice if I do a u substitution on this thing, x to the 10th, it's going to be pretty nice because we're going to get something like x to the 9th there. So we'll just start with that and we'll do u equals x to the 10th. du is just going to be 10 x to the 9th dx. So when I substitute, I'll multiply in the 10 to set up the du. And so I don't change it, I'll just divide off 10 out front here. So we'll go ahead and substitute. First, when you plug in infinity, of course that's still going to infinity. You plug in 2, now we get 2 to the 10th. And then all this stuff is going to simplify a lot now. So we have du in the numerator. This just becomes u squared minus 48u plus 575. But 575 is pretty nice because 24 squared is 576. So let's do this. But then if we have 24 squared minus 1, that's 575. Factoring that as a difference of two squares, you get 24 plus 1, 24 minus 1. And so this gives us 25 times 3. The reason that's helpful is 25 plus 3 is going to be 48. So what that's going to mean for us is that we can factor this denominator, just keeping all this other stuff around. How we can do it is writing it as u minus 25 times u minus 23. I don't think I need this, so we'll get some space. And then this is just going to be 1 du. So then this is perfectly set up for partial fractions. Of course, I always like to avoid it. So to avoid it, how we'll do it is, let's create cancellation just using these terms here. So I can write this, if I do something like kind of just forcing these terms into it, that's going to give us cancellation. If you do that out, the u's are going to cancel, but what you're left with is going to be 2. All this stuff here is 2. So in order that I'm not changing it, I'll just squeeze in a really skinny 1/2 here. And what that's going to allow me to do is now I can rewrite this integral just breaking it up into 2 integrals, breaking it on the minus sign, but then cancel, 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 cancel. And what's left is going to be 2 easy integrals. It's just going to be natural log of this and this. So let's see what happens. We have 1/2 natural log u minus 25. I'm going to drop absolute value because we're starting at 2 to the 10th, which is like 1024. So that's always going to be positive. And then we'll have this right here. But what I'll do right away is let's clean that up with log properties before I evaluate. So I'll just kind of leave that for now. But when we do that, we can write it as 1/2 natural log u minus 25 over u minus 23 evaluated from 2 to the 10th to infinity. Okay, now the infinity, that's going to be pretty nice because if you do it out as a limit, the constant part's not really going to matter. And so the inside part is going to be approaching 1, natural log of 1. The whole thing is going to be approaching 0. So we just kind of ignore that part. We're going to have a minus sign from the evaluation. Then plug in. Let's put it back to, let's think of this as 1024 for now. So then this is going to be natural log minus 1024 minus 25, that's going to be 999. And then this is going to become 1001. I can use this minus sign and just use it to flip it, take the reciprocal here, bring it into the exponent with log properties. But clearly, if I do it, I'm out of space. So let me clean up the board and we'll continue from this thing here. Okay, now this point here, this is about where I got to last year, where I had to stop. I mean, maybe I kept going and didn't release the video, but either way, I couldn't really proceed from here because think about it, when we put this back in, we've got a giant number here. I don't know what that is. That's more than like a trillion. That's a lot. But this number right here, what's inside here is barely greater than 1. So it's really close to 0. I don't know, I would need a calculator, but maybe it's something like this, or maybe this is something in the ballpark of 0.001. So I was thinking all we can really do is estimate. We've got large number times small number inside the floor. I was hoping it would be 0 if it was somehow less than 1, but it's definitely not. This is, if this is like 10 to the minus 3, this is 10 to the 20. So it's clearly going to be greater than 1. So I was kind of stuck. Anyway, doing it over again, I did find a way to continue. So we'll do that and hope for the best. So first, just cleaning this up and writing it a different way. We notice that it's very close to 1,000, numerator and denominator. 1,000 is 10 cubed, so I can write it like this. And then this step's a little weird, but I want to kind of reverse it. So I'll multiply in 1, doing this kind of thing. Distribute, multiply, do all that stuff. And what you get is it's going to become, with exponent properties, we're going to have 10 to 0 or 1. Just like this, we'll have 1 plus 10 to the minus 3, and then 1 minus 10 minus 3. The reason I do it this way is because now we have something that's in this form, natural log 1 plus x, 1 minus x, and we can use power series. There's a formula for this. I think I did a video on it, but let's just kind of redo it right now. Not all the way. I'm just going to assume that we know our power series formula for this one and this one, because with log properties, we could split this up, right, and write it like this, kind of putting it back to what we had before with this anyway. So what I'll do is expand each of these out individually with power series. And what you'll notice, the formulas are really similar. It's just that we have alternating signs on the 1 plus x, and then here we've got the negative out front. Now with this, again, using this, our x value is going to be 10 to the minus 3. So we're subtracting in order to get something in that form. So we're subtracting these, put it together. Here, minus times minus is plus, and then because we have alternating signs, all the even terms cancel out. Oh, sorry, I should have left that one, but I think you get what I'm saying. All the odd terms are going to remain, all the even terms cancel out. So putting this together, we're going to have 2 copies of all the odd terms. So 2 times x cubed and x to the 5th, etc. So using this formula and getting back to our problem, where we know what our x value is, what this is going to become is 1/2 times 2, which of course is going to cancel. And then we have our x value 10 to the minus 3. So this becomes 10 to the minus 3. I'll just leave it. I won't simplify it. So we're just going to have it all to these odd powers with odd numbers in the denominator like this. And so this right here, this is going to be our value for that integral that we started with. And all we need to do is we just now need to plug it inside of our floor function and try to finish it off. Okay, now from here, all I did was simplify dividing into 10 to get 10 to the 19th here. And now really to finish it, I just need to distribute in, and we'll have to apply the floor function, of course. So this isn't going to be too bad. 10 to the 19th times 10 to the minus 3 gives 10 to the 16th. Here, exponent properties there is going to become 10 to the minus 9. Multiplied in here, we get 10 to the 10 over 3. This becomes 10 minus 15 times this, 10 to the 4th over 5. And then here, that's 10 to the minus 21. Distribute with this, we get 10 to the minus 2, or like 1 over 100. And then, of course, this is still going on to infinity. But now let's look what we have left. The question with the floor function, if you have the floor function of where x is an integer, you just get back the x. If you have some decimal number like 3.4, let's say, that just rounds it down to 3. So looking at something like this, the concern is, I mean, if everything was an integer, we would just be done. The value would be the exact same, but we have to consider when is it an integer, when is it not. 10 to the 16 is clearly an integer. So is this, that's 10,000 divided by 5, that's an integer. But this is not an integer. And this is not an integer. This right here is 1 over 100 times 1/7 is 1 over 700. Now at this point, if we wanted to be really careful about it, we'd have to show that all these different fraction parts are less than 1. I think it's pretty apparent. I mean, you could do it out like geometric series or something, but everything over here, I mean, this is way less than 1, but all this stuff is going to be way less than 1, and inside the floor it's going to amount to 0. So without doing it really carefully, I'm going to say this is 0. Now this here is a little bit of a problem, but we know exactly how this works because, I mean, no matter any power of 10, you know, we have some number like this, and it's divided by 3. We always know that this minus 1 is an integer. Any number made up of 9s, this is always going to be divisible by 3. So applying the floor function on this, what we're going to get back is we're going to get back these integer values. And this one right here, it's going to be just over an integer, but we can correct it with just minus 1. So applying the floor function on it, what we're going to get for the first part is 10 to the 16, plus here we get 10 to the 10 minus 1, turning that into an integer. And then here this is already an integer, so we get 10 to the 4th over 5. I think in the MIT solution they multiply it out, but I just don't want to do that, so I'm just going to leave it like this and call it good. Okay, so I think you kind of see the dilemma with the floor function, but with power series it actually works out to something fairly nice, and you don't have to estimate it or use a calculator. Okay, that's it for today. Thanks everyone for watching. Have a good day.